Hello everyone, welcome to the second part of the video. In this video, we are going to continue the type of mechanisms for nucleophilic substitutions. In the previous video, in the part 1 video, we are talking about Sn1 mechanism. So now let's look at the Sn2 mechanism. So Sn2 mechanism is a bimolecular nucleophilic substitutions. That means in our rate determining step, it involves two molecules. So bimolecule refers to two molecules. So this is a second order reactions in which the reactions rate depends on the concentrations of both haloalkanes and nucleophile. So in our rate determining steps, we have both haloalkanes and nucleophile. So the rate law, we can write it as the rate equals to K times the concentrations of haloalkane and the concentrations of nucleophile, both raised to power 1. So the overall order of reactions is second order. And for this Sn2 mechanism, it only involves one step. So in these steps, nucleophile will attack straight away from the back side of our electrophilic carbon. Which is also means that it is from the side directly opposite to the halogens. So this is our rate determining step. So for this one-step mechanisms, there is one transition state, which involves the partial bonding between the attacking nucleophile and the halogens. So in this one-step mechanism, the backside attack of the nucleophile will cause the product formed to have an inversions of configurations at the electrophilic carbon atom. So these inversions of configurations will show it in the next example. So let's look at the questions, example questions number 1 for this Sn2 mechanisms. So first of all, we have this chloroethane, or you can also name it as methyl chloride, in which it will generate a methyl carbocation. So methyl carbocation does not favor for Sn1, therefore it will go with Sn2. So this OH minus will substitute the Cl minus, so it undergoes nucleophilic substitutions to give you the products and alcohol. Okay, so from haloalkanes into an alcohol, and then there is a leaving group Cl minus. So this methyl chloride will prefers to undergo Sn2 mechanism. So remember that just now in the previous slide, we talked about Sn2 mechanisms. It's only one step, but in this one step, it involves transition state. Okay, so let's look at the mechanisms here. So Sn2 means that in our rate determining steps, it involves two species, which is our nucleophile and the electrophile. So against the same thing, please label down your delta positive carbon, electrophilic carbon, and the delta negative chlorine. So from the OH minus your nucleophile, remember that the negative charge is on top of your oxygens. So moving from the oxygens, attacking the electrophilic carbon from the back, which is directly opposite with this CCl bond. So when the nucleophile attack from the back of this electrophilic carbon, you are going to break this CCl bond. So from the middle of the bonds go into the chlorine. So in the first steps over here, in which is involved the nucleophile and the haloalkane, is our rate determining steps. To form this transition state, pay attention to how you draw this transition state. There is a big bracket and then the structures inside with this staggered sign. Okay, so this transition state is actually a state before it forms your final product. So it's going to show the bond forming, okay, between your carbon and your nucleophile. Okay, CO bond begins to form. So we're using the dot sign over here to indicate the bond is forming. And then for the CCl bond, the bonds over here begins to break down. So again, there's a dot sign over here. So the other three bonding doesn't affect, so we just copy again. So for this nucleophile and the leaving group Cl, we are going to draw the delta negative signs on top of it. So delta negative oxygens and delta negative chlorine. And then after that, it's going to form your final product. So remember that the nucleophile is attacked from the back. So now the OH is at the opposite side. And then you will realize that the structures, the final products, has an inversions of configurations, which means that the products is kind of like a mirror image compared to your starting reactant. It's just that for this CCl bond is opposite directions for this COH bond. It looks like kind of like a mirror image, but with different substituents there. And of course, there's a leaving group, Cl-. So if it is an Sn2 mechanism, remember that nucleophile attack from the back and have the transition state. There's an inversions of configurations, and then the whole mechanisms need to draw in a 3D structures. So there's the characteristics of Sn2 mechanism. So for this Sn2 mechanisms, the activated complexes transition state as the intermediate. So this transition state in your one-step mechanism, and it required a strong nucleophile. The reasons why we require a strong nucleophile because you need this nucleophile to attack the electrophilic carbon from the backside. So it must be strong enough to push away the halogen as the leaving group. So the examples of strong nucleophile, you can see the table. This table is in the chapter 7's note, page 11. So example of strong nucleophile, if you can see OH minus, in which it's dissociate maybe from sodium hydroxides or potassium hydroxides. Or maybe you have this alkoxide ion. So for example, CH3O minus, your methoxide ion, ethoxide ion. And for this one, it's typing errors, yeah. For this is CH3ONA. Okay, CH3ONA. So that means you can see this alkoxide ion dissociate from the salt. Okay, also considered as a strong nucleophile. And then if you got Cn minus, your cyano ion. And then maybe you have this NaCN, which you got the Cn minus as well. KCN, you have a Cn minus. So this is the example of your strong nucleophile. And then for this weak nucleophile, you have H2O, you got alcohol, for example, methanol, ethanol, propanol, and etc. And maybe you have this ammonia, which is also considered as a weak nucleophile, as it is the weak base. And the extra weak nucleophile is this acetate ion. Okay, acetate ion with C double bond O minus. This is a weak nucleophile. So maybe you can get this acetate ion from a salt. So the salt, for example, is CH3COO-Na or COOK, wherever it combined with a positive ion. So this is considered as a weak nucleophile. So the order of reactivity for this Sn2 mechanisms, the least reactive will be your tertiary haloalkanes. And then increasing the rates for this secondary haloalkane, followed by primary haloalkane. And the most reactive one is your methyl halides. Okay, and as this methyl halides, it is a very simple structure, so it enables the backside attack. Okay, and why the tertiary haloalkane, secondary alkane, they have a lower reactivity? Because the backside attack of electrophilic carbon is hindered by the presence of the bulky alkyl group. So if you got alkyl group, even though CH3 is also considered a bulky alkyl group. Okay, it's hindered, that means it's blocked. Okay, it's blocked by the presence of this alkyl group. Therefore, your tertiary haloalkanes with 3 alkyl group present, so the backside attack becomes very difficult. Okay, so for Sn2 mechanisms, remember that steric effect is very important. So for this steric effect is the presence of the bulky alkyl groups. So for this steric effect, so sometimes we know as the steric hindrance. It refers to a chemical reactions will be slowed down or prevented because large or bulky groups for this alkyl group on the reactants molecule hinder the approach of another reactant. Okay, slow down the approach, prevent the approach, making the backside attack difficult. Some of the factors that determine the reactivity of haloalkanes towards this Sn2 bimolecular nucleophilic substitutions mechanism. The first factor is the steric effect or the steric hindrance at your electrophilic carbon. So we say that the tertiary haloalkane is more hindered than a secondary haloalkane than the primary haloalkane. So looking at this diagram, you will see, okay, this chlorine attached to a primary carbon. So you only got one alkyl group. Okay, so this is your primary haloalkane. And then for this one, your chlorine attached to a secondary carbon. So this is your secondary haloalkane. and then this chlorine attached to a tertiary carbon, so this one will be your tertiary haloalkane. So you can see that for this tertiary haloalkane is more hindered. So that means this CH3 methyl group block the backside attack of your nucleophile. So imagine that we need a nucleophile. So for example, this is your nucleophile. I need to attack from the back of your electrophilic carbon. Remember, at the backside means that is opposite to this Cl group. So this bulky group, it form a shield. Okay, it form a steric hindrance. So that means it kind of like blocking the pathway for this nucleophile to attack from the back. So we say that this tertiary haloalkanes, it make it very difficult for the nucleophiles to attack from the back. So it's impossible for Sn2 mechanisms to happen. The second factor is due to the presence of alkyl group at neighboring carbon. So this is also related to steric effect. But the first factor just now is directly on the electrophilic carbon, and this second factor is at the neighboring carbon. So for example, if you look at these structures, the chlorine is attached to a primary carbon. So actually for these structures, it is a primary haloalkane. So the presence of alkyl group at the neighboring carbons refers to the carbon which is next to your electrophilic carbon. So if you look at the carbons over here, if we try to draw the delta positive, delta negative, this carbon will be delta positive, and then here will be your delta negative. So now we are looking at the neighbor carbons. So for these neighbor carbons, there is a presence of alkyl groups. So even though we want to attack this electrophilic carbon from the back, but because of the presence of the alkyl group, it's also forming a shield behind it. So also kind of the same like it blocked the backside from nucleophilic attack. So nucleophile is very difficult to attack from the back. Okay, so this will prevent the backside attack by nucleophile and slow down the reactions. So in this case, the reactions will proceed via Sn1 mechanism as rearrangement is possible. So you imagine after you break up the bonding between carbon and Cl, so you form a primary carbocation. So after you do a 1,2 methanide shift, you're going to form a tertiary carbocation. This is in another words, first you form the primary carbocation, then do rearrangement to form a more stable tertiary carbocation. Okay, so you have to check whether there's any steric hindrance or not at both electrophilic carbon or the neighboring carbon. So let's try the example questions number 2. So given in the questions, you have 2 bromobutane and NaOH. So this is the structures of your 2 bromobutane. So bromine, which attaches to the secondary carbon, and this is our secondary haloalkane. Secondary haloalkane, it can proceed with both Sn1 and Sn2. So we look at this NaOH. Okay, so this NaOH is a strong nucleophile as this is an ionic compound. We have Na positive and OH minus. So when you see OH minus, it refers to a strong nucleophile. So let's predict the structures first. The OH will substitute the bromine to give you an alcohol. And then there's a side product, NaBr. So since nucleophile is present, therefore for these reactions, it will proceed via Sn2 mechanism. So there is a tips for you. For a secondary haloalkane, it can proceed both Sn1 and Sn2. Okay, so it depends on what nucleophile do you have. If it's a strong nucleophile, then it will proceed via Sn2 mechanism, because strong nucleophile is strong enough to attack the electrophilic carbon from the back. So again, the same thing. Here's your electrophilic carbons and the delta negative bromine. So if this one is an Sn2 mechanism, you need to draw out in 3D structure. Okay, so this is the structures for your 2 bromobutane. Okay, and then this is your electrophilic carbon, and then your delta negative bromine. And then the other one, you just place it randomly. So you have a CH3 over here, you have CH2, CH3, and then you have another one which is hydrogens. If you were to use skeletal structures, so you will just leave it like this. the one that doesn't write anything will be your carbon. And if it's hydrogens, then you just put a hydrogens atom here. Alright, so in your first step, which is your rate determining steps, it involves both nucleophile and haloalkane. So remember that nucleophile will attack from the back for this Sn2. So from your oxygens over here, attacking your electrophilic carbon, and then push away the bromine. So you are forming the transition state. Okay, this is your transition state where the bond forming between carbon and oxygens, and then bond breaking between carbon and bromine. So remember to write out your delta negative on oxygens and delta negative on carbon. The remaining three bondings, it's follow exactly the same as how you draw it in the first structures, and then followed by the final products. So now it complete forming the bond between carbon and oxygens, and then there is a leaving group Br-. So this Br- will then combine with your Na+ in the nucleophile to form this side product NaBr. So for your mechanism, you just draw it like this, in which we just use the nucleophile OH-. Okay, so from the mechanism here, you can clearly see there is an inversions of configurations. So please have a try at questions number 3 and questions number 4. For questions number 3, Madam have give you the clue for these equations, okay, between the haloalkanes and the NaOH, the strong nucleophile. It involves rearrangement and will proceed via Sn1 mechanism. Okay, so have a try, have a look. Remember to identify what is the class of haloalkane and what is the strength of your nucleophile. So have a try questions number 3 and 4 and will be discussed during our tutorial sessions. So now we want to look at the comparisons between Sn1 and Sn2 mechanism. So for Sn1 mechanisms, the rate of reactions is proportional to concentrations of haloalkanes only. So Sn1 is a first order reactions. So rate equals to K concentrations of haloalkane raised to power 1. This one is the rate law. And then for Sn2 mechanism, the rate of reaction is proportional to the concentrations of both haloalkanes and nucleophile. So this is a second order reactions, in which the rate law is rate equals to K, concentration haloalkane raised to power 1, concentrations of nucleophile raised to power 1. And then for Sn1 is a two-step mechanism, Sn2 is a one-step mechanism. So the order of reactivities for this Sn1 mechanisms, tertiary haloalkane is the most reactive, followed by secondary haloalkane. Primary and methyl halides are unlikely. So for Sn2 mechanisms, the order of reactivity, the most reactive goes to methyl halide, followed by primary haloalkanes. Secondary haloalkane is also possible, depends on what is your nucleophile. But then tertiary haloalkane is unlikely, okay, due to the steric effect. Next, for Sn1 mechanism, nucleophile strength is not important. That means doesn't matter whether you are using a weak nucleophile, strong nucleophile. For Sn1, it doesn't matter. But for Sn2, yes, it must be a strong nucleophile. And then for Sn1 mechanism, carbocation as intermediate. And then Sn2, you have your activated complex at transition state. If you still remember the one with bracket and then the structures with the partial bonding in between. Okay, and then for Sn1 mechanism, since it involves carbocation as intermediate, therefore it might involve rearrangement. So either 1,2 hydride sheaf or 1,2 methanide sheaf. But for Sn2, no rearrangement is possible. And then for Sn1, steric effect is not important. And Sn2 steric effect is important as the nucleophile need to attack from the back. So after comparing between Sn1, Sn2, and you roughly know about the characteristic of both mechanisms, so there's an overview for you to determine the type of mechanisms. To determine the type of mechanisms is whether it is an Sn1 or Sn2 mechanism, you have to think of a few factors. So first of all, what is the class of haloalkane? Is there any steric effect? Is there any rearrangement possible? What is your strength of nucleophile? Okay, so you need to consider these factors. So if let's say in the questions you see a methyl halide, so methyl halide is the most reactive towards Sn2 mechanism as it doesn't have any steric effect. Okay, so Sn2 mechanism for methyl halides. If you have a primary haloalkane, you need to consider is there any steric effect. If there is no steric effect, so that means backside attack is possible, therefore it will proceed via Sn2 mechanism. But if this as a primary haloalkane has steric effect, okay, with steric hindrance, steric effects, that means the backside attack is impossible. Therefore, we need to do rearrangement to proceed via Sn1 mechanism. So the one with steric effect, normally it will involve rearrangement. And for this secondary haloalkane, because it will undergo both Sn1 and Sn2, it has a roughly reactive towards both mechanisms. So you have to look at the strength of nucleophile. If you have a strong nucleophile, so remember strong nucleophile is required for Sn2. So it will attack from the back and then push away your leaving group. So proceed via Sn2. If in the equation, so in the questions, it gives you a weak nucleophile. So weak nucleophile, you can only choose to proceed via Sn1. So that means you form a carbocation and then after that react with this weak nucleophile, and then this is Sn1 mechanism. And then lastly, also very easy, if you got a tertiary haloalkane, so this one definitely you are going to form the very stable tertiary carbocation. Therefore, this is an Sn1 mechanism. So that's the end of our chapter 7. Please have a try at your questions number 3 and 4 and the remaining exercises. So I'll see you again in the next chapter.